What we are starting with in this lecture is about the abnormal molar mass. Now, if you remember, one of the important application of the colligative properties is to calculate the molar mass of the solute. So one of the important application of the colligative properties is to calculate the molar mass of the solute. Then what is this abnormal molar mass? First of all, let's see. Molar mass, which is either higher or lower than the expected molar mass, is called abnormal molar mass. So molar mass, let's say we calculate the molar mass of a solute using a colligative property, and that molar mass comes out to be either higher or lower than what it was expected, then such molar mass would be referred to as the abnormal molar mass. I'm just giving you an example. If you consider NaCl as a solute, then for NaCl, the molar mass of solute, I'm considering NaCl as the solute. The molar mass should be the atomic mass of sodium, which is 23, plus the atomic mass of chlorine, which is 35.5, and this should be equal to 58.5 grams per mole. Okay, so this 58.5 is the expected molar mass for NaCl. But when you get this molar mass either less or more than 58.5 grams per mole, then that molar mass will be regarded as the abnormal molar mass. Now we are going to look at the reasons for this abnormal behavior or reason for this abnormality in the molar mass. Why is the molar mass coming out to be either higher or lower than the expected value? There are two reasons behind it, and we'll look at it one by one. The first reason which is behind this abnormality is the dissociation of the solute. It is the dissociation of the solute particles in the solution. I will take an example. Let's say potassium chloride is added as a solute. So KCl is added as a solute to, let's say, water to make a solution. Now KCl is an ionic compound and it has a tendency to dissociate. The moment you will add it to water, it will dissociate to give K plus ions and Cl minus ions in the solution. So we'll have these two ions produced. Now, if you consider here how many moles of KCl is taken, then the answer is there is 1 mole of KCl being taken. And after dissociation, we are getting 1 mole of K plus ions and 1 mole of Cl minus ions. So, I have taken 1 mole of KCl. But finally, in the solution, I am getting 2 moles of the ions. What I am getting is 2 moles of ions in the solution. Now, if you remember, what are colligative properties? The definition of colligative properties itself is that these are the properties that depend on the number of particles irrespective of their nature. This we have already discussed in the earlier lectures. So colligative properties, they depend on the number of particles irrespective of their nature. And what has happened because of dissociation, the number is increased. From 1 mole of particles to now we have moved to 2 moles of particles. So what will happen? When colligative properties depend on the number of particles, so you can say that when there is dissociation in solution, Okay, what will happen? Dissociation will lead to increase in the number of particles. As you have seen in the case of KCl, one KCl molecule is dividing itself into two particles, K plus and Cl minus. So the number of particles are getting increased. So on dissociation, there will be increase in the number of particles. If there will be increase in the number of particles, certainly there will be increase in the value of the colligative property also, because we've already seen that colligative properties are directly proportional to the number of particles. The more the number of particles in solution, the greater will be the value of the colligative property. So on dissociation, there will be increase in the number of particles, and therefore there will be increase in the colligative properties. Also, this increase in the colligative property results in a decrease in the molar mass of the solute. Okay, when the number of particles increase and when the colligative property will increase, the molar mass of the solute is going to decrease. Now let me explain this, how this will happen. You take any colligative property. For that matter, I am considering delta TB, elevation in boiling point. If you remember, delta TB is equals to KB into M. M is molality, and which you further write KB into weight of the solute upon molar mass of the solute, weight of the solvent that you have to take in kilograms. Now, how do you see the molar mass of the solute? This is MB. This is the molar mass of the solute, and this is your colligative property. How are the two related? As you see, delta TB is inversely proportional to the molar mass. The colligative property is always, I have taken example of delta TB, you may take example of delta TF, or you may take example of the osmotic pressure or the relative lowering in the vapor pressure, any colligative property. Okay, every colligative property is found inversely proportional to the molar mass, and that is why I said here, when the colligative property increases, molar mass decreases, because the two are what? Inversely proportional to each other. So again I am repeating, when there will be dissociation, there will be increase in the number of particles in the solution, and there will be increase in the value of the colligative property. But because colligative property and molar mass are inversely proportional, there will be a decrease in the molar mass of the solute, and this decreased molar mass is the abnormal molar mass. So why the molar mass is abnormal? It's because of dissociation of the solute particles in the solution, which is increasing the number of particles in the solution. Now let's consider the second possibility because of which there can be this abnormality, and that second possibility is association. Association of the solute particles in the solution. So let's take an example of ethanoic acid. Ethanoic acid is CH3COOH. When ethanoic acid is taken in the presence of a non-polar solvent, okay, when it is taken in the presence of a non-polar solvent, it is found to associate. Associate means what? Two molecules or 2 moles of ethanoic acid that you take. I am taking 2 moles of ethanoic acid and I have added it to a non-polar solvent, and what is found is that the two molecules, they associate. CH3 C double bond OOH is one molecule, and CH3 C double bond OOH is the second molecule. So these are the two molecules, and what happens? This hydrogen and this oxygen, they enter into hydrogen bonding. Likewise, this oxygen and this hydrogen also enters into hydrogen bonding. So what is this? This is intermolecular hydrogen bonds, and because of that, the two molecules have associated, they've joined together, and this bigger molecule which is formed is a dimer. Di means two units joined together, and now this will behave as one. So from 2 moles I have reached to 1 mole. I started with 2 moles of ethanoic acid, but I am getting only 1 mole of a final thing here. And what is that one final product formed here? You can say it is the dimer, where 2 molecules have joined together through hydrogen bonding. So I started with 2 moles, but in the solution it's actually behaving as 1 mole. So what has happened? Because of this association, what do you see? When there is association of particles, when the particles join together, what happens? There is a decrease in the number of particles. There is a decrease in the number of particles, as you see, from 2 moles to 1 mole. It has got half, right? It has become half of what it was initially. So from 2 moles to 1 mole. There is decrease in the number of particles, and so there will be decrease in the colligative property. You know, colligative properties are directly proportional to the number of particles. So when the number of particles are going to decrease, the colligative property will also decrease. And as we have already discussed, that colligative properties are inversely proportional to the molar mass. I explained to you here that delta TB is inversely proportional to molar mass, like that every other colligative property is also. So inversely proportional, so there will be an increase in the molar mass, and this increased molar mass is nothing but it is the abnormal molar mass. So what was the reason behind this abnormality? Association. Because of association, number of particles got decreased, so colligative property decreased, and therefore there will be an increase in the molar mass of solute, which is now regarded as the abnormal molar mass. To lift up this abnormality in the molar mass, which is because of the dissociation or the association of the solute particles in the solution, Vant Hoff introduced a factor which is known as the Van 't Hoff's factor, represented by the symbol small I. So the Van 't Hoff's factor is going to take care of the dissociation and the association extent. So what is Van 't Hoff's factor going to do? It is going to, you can say, account for the extent of dissociation or association of the solute, and will help us to get the correct value of the molar mass. Now this Van 't Hoff's factor is defined in 3 ways, and it can be calculated using these 3 formulas also. The Van 't Hoff's factor I is defined as the normal molar mass upon the abnormal molar mass. The normal molar mass is the one that you expect, okay, and the abnormal molar mass is that you get experimentally. So the abnormal molar mass is the one that you will be getting through experiment. So it's the experimental molar mass, and the normal is the one which you can just calculate by looking at the formula, the molecular formula of the particular solute. Second formula which can be used to calculate I is the Van 't Hoff factor is also defined as the observed value of the colligative property, divided by the calculated colligative property. Okay, so I is defined as the observed colligative property divided by the calculated colligative property. Here, the observed colligative property is the one which is experimental, that you get the value through the experiment you observe, and the calculated colligative property, certainly we calculate, and we calculate with an assumption. The assumption is that there is no association or dissociation in solution taking place. So observed is the one that you will observe, that is the experimental value, and calculated colligative property we will have to calculate with an assumption that there is no association or dissociation of the solute taking place in the solution. And there is one more formula, third formula, to calculate the Van 't Hoff factor, which is, it is also defined as the number of particles after association or dissociation as the case may be, divided by the number of particles before association or dissociation. Number of particles after association or dissociation divided by the number of particles before association or dissociation. So the Van factor can be calculated by using these three formulas. Either we can use the molar mass, or we can use the colligative property value, or we can use the number of particles in the solution after and before association or dissociation. Now further, let's say alpha represents the degree or the extent, of association or dissociation. Alpha is the degree of association or dissociation. Then it is related to the Van factor. How? We'll just discuss here. Let's take dissociation on the left side and association on the right hand side. In case of dissociation, alpha is equals to I minus 1 upon n minus 1. You know alpha already, it will be the degree of dissociation. I is the Van factor, and what is n here? N in this formula is the number of particles after dissociation. The number of particles after dissociation. Like when KCl dissociates, it gives K plus and Cl minus. So how many particles after dissociation? 2 particles after dissociation. So their N will be taken as 2. On the other hand, if it is the case of association, then alpha is equals to I minus 1 divided by 1 upon n minus 1. And what is N here? N in this case is number of particles undergoing association. Number of particles undergoing association. That's the value of N in case of association. Like if 2 particles or 2 molecules of ethanoic acid join together to form a dimer. So because 2 particles are joining together, you will take the value of N equals to 2. How many particles are joining together to form the final form, and how many particles do you get after the dissociation process? So that's N in the 2 cases. Now further, when there is 100% dissociation in the solution, if it's a case of 100% dissociation, now what do you mean by 100% dissociation? Alpha is equals to 100%, which means alpha is equals to 1. And if I substitute the value of alpha equals to 1 here in this formula, then what will I get? If alpha equals to 1 here, I minus 1 will be equal to n minus 1, or you can say I is equals to n. So if you are given that there is 100% dissociation, then the value of the Van factor will be straight away equal to n, where what is n? The number of particles after dissociation. Likewise, if you use the same thing here, when there is 100% association in the solution, again alpha 100%, which means equals to 1. Now if you put alpha equals to 1 here, what will you get? I minus 1 equals to 1 upon n minus 1, and this gives us I equals to 1 upon n. So here the value of Van factor will be straight away equal to 1 upon n, where what is n? N is again the number of particles which were undergoing association. One more fact that you can note down here is, when the value of Van factor is equals to 1, whenever Van factor is equals to 1, this indicates that there is no dissociation or association in the solution. When Van factor is 1, there is no association or dissociation. When the value of Van factor is more than 1, then this is the case of dissociation, or you can say whenever there will be dissociation taking place in the solution, Van factor will be greater than 1, and whenever the value of Van factor is less than 1, then this is the case of association. So through the value of the Van factor, you can identify if there is association dissociation or nothing taking place in the solution. So when Van Hoff's factor is 1, no association or dissociation. When it is more than 1, it is dissociation. When it is less than 1, it is the case of association. I am explaining how to identify the value of n in dissociation and association by taking one example each. I was explaining that let's say the solute was KCl, which when added to water dissociates to give K plus and Cl minus, right? So in this case, n will be considered as what? 2, because you get 1 plus 1, 2 particles. So for this case, the value of n has to be taken as 2. Now suppose you have MgCl2 and MgCl2 was added to water and it dissociates to form Mg2 plus and 2Cl minus. So here the value of n has to be taken as 1 plus 2 equals to 3. So what is n? And these are the cases which I have mentioned here for dissociation. So whenever there is dissociation, how will you identify n? N is number of particles after dissociation. Like here it is 1 plus 1, 2, and in this case it is 1 plus 2 equals to 3. Let me give you one more example of association also, and that is the case of ethanoic acid. When you take CH3COOH ethanoic acid 2 moles and it forms CH3COOH whole twice, which means this is now the dimer. This is the dimer in which the two molecules of acetic acid, they have joined together to form this bigger molecule dimer. This is now behaving as one unit. Earlier it was 2 units, now it is behaving as 1. Why? Because this is the case of association. Particles have associated or they have joined together. So what is n here? What is the value of n? In association, as I told you, n is equals to what? The number of particles undergoing association. So see here, how many particles are undergoing association? It's 2 particles. So the value of n here also is going to be 2. The number of particles undergoing association. It's 2 particles joining together to form 1 unit. Therefore, n equals to 2. I'll give you one more hint. Whenever in a question for association you see that dimer is being formed. So when the term is dimer, now di means 2 units. So dimer means 2 units joined together. So here the value of n equals to 2. Suppose it was mentioned that a trimer was formed. So when a trimer is formed, that means how many units joined together? 3 units. So you will take the value of n equals to 3. And it can even be that a tetramer was formed. Now tetra means 4. So 4 units were joining together. So you will take the value of n equals to 4. So this is how in case of association, you can identify the n value to calculate alpha, the degree of dissociation or association. Now we are winding up this topic by rewriting all the colligative properties now. So all the colligative properties now will be written incorporating the Van Hoff's factor, because if you don't incorporate the Van Hoff's factor, the value of the molar mass is going to be abnormal. Either it will be higher or it will be lower. But if you incorporate the Van Hoff's factor, you will get the correct value, because Van Hoff's factor is the correction term that takes care of the association and the dissociation extent and gives us the correct value. So we have talked about 4 colligative properties. So number 1 was the relative lowering of vapor pressure. So this was our first colligative property, and the expression for it was delta P by P1 naught is equals to chi B. If you can recollect, the relative lowering in vapor pressure is equals to the mole fraction of the non-volatile solute. But now that will be changed to I times of chi B. So delta P by P1 naught equals to I into chi B. All the terms we have already studied in the previous lectures. So I am not rewriting it here. The second colligative property was elevation in boiling point. And elevation in boiling point was equal to delta TB, which was further equal to Kb into M molality. And now the change expression is going to be delta TB is equals to I KBM. Likewise, the third colligative property was depression in the freezing point. And now the depression in freezing point colligative property with the change incorporated, correction term incorporated, is going to be delta TF is equals to IKF into M. And the last colligative property that we have studied here is osmotic pressure. Osmotic pressure, which was represented by the symbol pi, and now pi will be equal to I into CRT. So what you see here is that all the colligative properties now must incorporate the Van Hoff's factor I, without which the calculations will be incorrect. So no question on colligative property is to be solved without using the Van Hoff's factor. Only if it is mentioned that there is no association, no dissociation, and that is the case when you have non-polar solutes, the ones which cannot dissociate or cannot associate, then the value of Van Hoff's factor can be taken as 1. Otherwise, if it's an ionic salt or if it's an acid like ethanoic acid which can associate or dissociate also in water, you have to consider the Van Hoff's factor to calculate the value of the colligative properties.